All right, let's talk about colligative properties. Colligative properties refer to the fact that mixtures will have different boiling points and freezing points than their pure components will. For instance, ocean water, because it's so salty, has a much lower freezing point than pure water does. It's going to take a much lower temperature to freeze ocean water. Similarly, if you boil salt water, that's going to affect the temperature at which the water is going to boil compared to pure water. So I'm going to tell you the formulas that give us that information. If we have a change in the freezing temperature, so this is a shift in the freezing temperature, that's going to equal negative Kf multiplied times M solute. Okay, let's break these down. This Kf right here is called the freezing point depression constant. Okay, and this is specific to the solvent. So if we're talking about salty water here, then this would be Kf for water. And what's the little m solute here? This is the molality of solute. You may or may not have learned about molality. I'm assuming you have, but remember that molality is the moles of the solute divided by kilograms of solvent. Notice that this is not the same as molarity, which is moles of solute per volume, liters of solution, total solution. This is the kilograms of the solvent. Now, if you look in the book, then you can see a nice explanation for ideal solutions. This freezing point depression constant equals R times the molar mass of the solvent, the fusion temperature squared. Remember, fusion is melting, divided by delta H of fusion. And this is for ideal solutions. So that's fusion, freezing. Let's take a look at the boiling point. Which will always increase with solute concentration. Okay? Very similarly, the increase in the boiling point, or the change in the boiling point, is going to be equal to Kb, again, times the molality of the solute. But this Kb is called the boiling point elevation constant. And the counterpart for ideal solutions that the book lays out is that this boiling point elevation constant is equal to R times the molar mass of the solvent times the vaporization, or the boiling temperature, squared, delta H of vaporization. Okay? This is again for ideal solutions. The last thing I want to say is that you can relate these two temperature changes to each other. So if we have a change in the freezing point, and then we have that freezing point depression constant, this is going to equal the molality of that solute, which just so happens to equal that change in the boiling point divided by that boiling point elevation constant. So another way to say this is that that shift in the freezing point is just an algebraic relation between that freezing point and boiling point elevation depression constants times that change in the boiling point. So now we're going to begin to delve into non-ideal solutions, and we need to lay this foundation in order to look at the equilibrium of non-ideal solutions. We saw before that the chemical potential of a certain component in a solution is going to be equal to the chemical potential of that pure component plus RT log partial pressure of that one over the vapor pressure of the pure substance. And for ideal solutions, we used Raoult's law, which, remember, is the partial pressure of the component in the mixture is equal to the mole fraction of that component times the vapor pressure that that component would be if it was pure. And another way to write this is that the mole fraction is equal to that partial pressure divided by that vapor pressure. And we saw also that for ideal solutions that the chemical potential was a little bit easier to deal with because we're going to be dealing with mole fractions, not with partial pressures. RT log XI, like so. However, our problem is that for real solutions, that partial pressure is not going to be equal to the mole fraction times that vapor pressure. Okay? So we're going to need to take an approach similar to we did with fugacity and introduce activity. Okay? So for solutions, that activity is going to equal that partial pressure divided by that vapor pressure. So it takes the place of X in this equation up here for ideal solutions. Okay, so this activity is like a mole fraction. Similarly to how fugacity was like a pressure for the real gases. Okay, so let's relate this activity to the actual mole fraction. The activity is going to equal gamma I xi, okay? And this gamma, kind of similar to the fugacity coefficient, is called the activity coefficient. And it's related to the degree of non-ideality of this solution. So what is the activity for a given solution, you may ask? And the answer is that just depends on the nature of the solution. You might be able to find this empirically through experiments and then just fit a curve of the activity. We saw a similar problem to that in chapter 7. And it is also possible to get the activity through theoretical means. And that is the method that we're going to use in chapter 10. We'll be looking at the activity of a electrolyte solution. So just sit tight and we'll get to see a real life example of this activity and this activity coefficient in the next chapter. Now, the last thing I want to tell you about today is Henry's law. And Henry's law is related to what we were talking about in the last slide, where it gives us the mole fraction of a particular component as equal to the partial pressure of that component divided by some empirical constant. Again, so you might find this experimentally, or you may be able to find it theoretically. This K is called the Henry's law constant. And I want to show you where this comes in. First of all, we ask, when is Raoult's law valid? The answer is, of course, it's valid when the solution has weak interactions, or interactions that are not significantly different upon mixing than when they're pure. I'm talking about enthalpic interactions. So the delta H of mixing is equal to 0. However, it is also valid when the mole fraction of our component is very close to 1. That's also when Raoult's law is valid. So then when is Henry's law valid? Turns out that Henry's law is valid when this mole fraction is very close to 0. So let's draw a little plot here. Let's say that I have the mole fraction of component A in a binary mixture, so that's A and B. And then over here, I'm going to have the partial pressure of that component A. All right? So whether we're talking about a real or an ideal solution, hopefully you agree that if the mole fraction of A is 0, then its partial pressure is going to be 0. And then if the mole fraction of A is all the way over to 1, then that right there is the vapor pressure of just pure A. Okay? Now I'm going to draw a dotted straight line here. This represents what the ideal solution partial pressures would predict. However, in reality, the curve that we're going to see is going to look fairly different from that. It's going to come up like this and then slowly taper off and go like that. So this is the real solution curve right there. So as you can see, right over here, where the mole fraction is close to 1, then Raoult's law is pretty well obeyed right there, because that dotted line is Raoult's law. But now let's take a look at Henry's law. Henry's law says something like that. This is Henry's. And as you can see, up close to this region right here, Henry's law does a pretty good job of describing how that curve goes. It's kind of a steep line for a little while, but then it eventually curves away. And if you have a medium valued mole fraction, then you can't use either one of those laws. You've got to use a more sophisticated theory in order to get that activity.